Okay, let's unpack this. Imagine you're gearing up for those crucial ATPL theory exams. Or maybe you're just like me, insanely curious about what truly makes an aircraft engine tick. That whole intricate dance of air and fuel that actually generates the power. Today, we're taking a deep dive into something absolutely fundamental yet often overlooked in just how clever it is: piston engine fuel injection systems.
Indeed, yeah. Our mission today is really to cut straight to the core. We want to give you a robust roadmap to understand these essential systems. We're here to extract the most important nuggets of knowledge, really, from our source material on piston engine fuel injection systems.
Hmm.
The goal is to arm you, our listener, with not just the theoretical understanding for those exam questions, but also, a solid practical grasp of how fuel gets from the tank to the cylinders efficiently, reliably, and crucially, safely.
And we've got some fascinating insights lined up. Insights that will not only prepare you for those tricky questions, but might also give you a real aha moment about the brilliant engineering involved here. We'll be focusing heavily on the specifics of indirect fuel injection, which is, you could say, the unsung hero in many aircraft piston engines. And then later on, we'll even peek into the advanced world of common rail systems, which are really redefining what's possible. So let's get started on this deep dive. Okay. So for many of us, I think, when we think about how fuel mixes with air in an engine, the carburetor is often the first image that springs to mind. It's that classic, almost iconic piece of machinery, isn't it?
It is.
But in aviation, particularly with piston engines, we often see something different, something with some pretty compelling advantages that, well, directly address the unique demands of flight. So what exactly is this indirect fuel injection we're talking about, and what's the fundamental shift in philosophy, away from a carburetor that makes it such a preferred choice in aircraft?
Yeah, that's a brilliant starting point, actually, because understanding that shift from carburetors immediately highlights the ingenuity of indirect fuel injection. At its core, indirect fuel injection, specifically the low-pressure continuous flow type we mostly see, it fundamentally moves beyond the limitations of a carburetor. So instead of relying on the Venturi effect, which is essentially, airflow creating a low-pressure area to suck fuel in the system, actively sprays fuel into the induction pipe, and it does it under pressure.
Oh, okay, so it's pushing it in, not pulling it.
Exactly. Think of it this way. A carburetor is a bit like sipping through a straw, right? The suction draws the liquid. Fuel injection, by contrast, is more like actively squirting a precise stream. It's a low-pressure continuous flow system. That means fuel is sprayed continuously into the induction pipe. And crucially, the injection point is as close to the inlet valve as possible.
Okay, why so close?
Well, that proximity ensures immediate mixing with the incoming air, optimizing the air-fuel ratio right before it enters the combustion chamber. The beauty of this approach, again, is that it injects fuel under pressure directly into the intake, rather than just letting airflow dictate the fuel supply passively.
Right, so it's a much more proactive and precise way to get the fuel where it needs to go, rather than just relying on airflow. That sounds like it would naturally lead to some pretty significant benefits, especially when you consider the incredibly dynamic environment an aircraft engine operates in, sea level to high altitude, idle to full power. So this brings us to a really key point for exams. When an engine is fitted with a fuel injection system like this, what are the core advantages that truly stand out? What makes it such a game changer for flight safety and performance?
You've hit on the key aspect there. When an engine is fitted with a fuel injection system of this indirect type, several advantages emerge that are just absolutely critical for aviation. Let's break them down, because these aren't just abstract points. They have profound practical implications for you as a pilot. First, think about the low operating pressure involved. We're generally talking about pressure somewhere in the range of, say, 15-20 psi within the system itself.
Well, that's quite low, isn't it, compared to some systems?
It is, relatively speaking. And this simplifies the design enormously. It reduces stress on components, makes the system less prone to leaks or, catastrophic.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best.